Hello and welcome to Textbook Engineering Problem. Today we're working out of Elementary Principles of Chemical Processes, 3rd edition. We're doing problem number 2.37. I'll read the problem statement. In modeling the effect of an impurity on crystal growth, the following equation was derived. G minus GL, GO minus G equals KL and C to the M. Okay, where C is impurity concentration, GL is a limiting growth rate, GO is the growth rate of the crystal with no impurity present, and KL and M are model parameters. In a particular experiment, GO is this value and GL is this value. Okay. Growth rates are measured for several impurity concentrations C in parts per million. With the following results. Okay, they give us a table of values. So we'll probably move to the computer to input those and use those. So for part A, we want to determine KL and M, giving both numerical values and units. Okay, in order to do this, we need to change our model. We'll change it into a linear model. And then from there, we'll calculate what KL and M are by putting those into our parameters. Okay, well, KL and M, I don't like that they're in the denominator. So maybe we can just flip this equation. GO minus G over G minus GL equals the reciprocal of this, which is KL C to the M. Okay, I think, yeah, this looks a lot like we can just take the log of both sides. So natural log of GO minus G divided by G minus GL. Something that we've done in past problems is we've kind of moved this denominator over to the other side of the equation. We don't want to do that in this case, and the reason for that is because G is, we kind of want to separate our variables. You don't have to do this in every case, but it does make it, I don't know, I think it makes it a little more, a little more like a line, because if you remember, the equation for a line has y's on one side and x's on the other side. So in my mind, when I'm making a linear model, I kind of look for that, and so I'm going to leave this term over here because it has a G in it, and so does it. It also has a G in the numerator as well. So I'm just going to leave that one as is and say that that is what y is. Then we take the log of the other side, and we have the log of the product. So I'm going to move that m down from being an exponent, and I'm going to put KL. Okay, and that's our equation for the line. So y equals this big thing, G naught minus G over G minus GL, and x equals the natural log of C, M equals M, believe it or not. All right, and B equals ln KL. Okay, so that's our model for the line. We'll put the values into the computer so we can do the linear regression there, because they already have the functions built in to do it, and it's kind of a pain in the butt to do it by hand. So I am not going to spend a bunch of time doing that by hand for you guys. But the equation is in the back of your book if you want to do it by hand. All right. Okay, we've switched over to the computer here. We've got, let's put in our constants first. So we've got G naught and GL given to us in the problem statement. So let's plug those in. G naught is 3e to the minus 3. Yeah. And GL is 1.8 e to the minus 3. Okay, we're determining what M and B are. So those are our parameters. Let's plug in our table of values. We've got C in ppm and we've got G in millimeters per minute times 10 to the 3. Okay. So I'm going to shift to those units so that they're not times 10 to the 3. So we'll say this is times 10 to the 3, and then we'll make an actual G column over here. Okay, 1.9. And then we'll shift these over. So that they're of the correct magnitude here. Okay, now let's create our y and x variables. So y equals the natural log of a numerator and a denominator. And the numerator is GO minus G. And the denominator is G minus GL. So those are our y's. And our x values are the natural log of C. Okay. M is equal to the slope of this line, known y's, known x's, and B is equal to the intercept of this line, known y's, known x's. There you go. Now we know what M equals. So M equals 2.48 and B equals minus 10.04. Okay, we need to find out what KL is though. And KL is equal to e to the minus 10 power. So now we know what KL is. So that means KL equals 4.34 times 10 to the minus 5. Okay, so if we want to find out what the units are of M and KL, so if we're examining our equation here, we know that M is an exponent, and exponents cannot have units, so M is unitless. So we know M equals 2.48, and it is no units. Unitless. Okay. KL, on the other hand. Okay, so we're examining KL's units, and we're examining our function here. We know that M is unitless, but we know C has units of ppm. If we look over on this side of the equation, we have, in the numerator, we have units of millimeters per minute, and in the denominator we have units of millimeters per minute. So those two units should cancel out. So the left-hand side is unitless. So that means that KL has to cancel out the units of C so that we end up with something that's unitless. Okay, so let's write that mathematically. We've got millimeters per minute in the numerator. We've got millimeters per minute in the denominator. Then we have unknown units here for KL. And then we have ppms raised to the m power. And the m's are unitless. Okay, so now we have to solve this algebraically. These units cancel out, and we're just left with KL's units equal ppm raised to the minus m power. So those units will cancel out as well, and we're left with no units. Okay, so that's the units of KL. Okay, so we've given both the values and the units of KL. So that answer is part A. So let's move on to part B. A solution is fed to a crystallizer in which the impurity concentration is 475 ppm. Estimate the expected crystal growth rate in millimeters per minute. Okay, so we'll just use our model and we'll calculate what if C equals 475 ppm, we'll use our model and we'll calculate what G equals. Okay? Okay, so we'll start plugging in our numbers here. So we know that C equals 475. We know that X equals 6.16 because of that. And Y equals, so we can't use this function because this function is not our model. So we have a linear model that we're using. Our linear model is Y equals M times X plus B. Okay, so that's our model for Y. Then we convert Y into G. And we can solve for G as a function of Y analytically. So Y equals the natural log of GL minus G divided by G minus GL. And this equals 5.26. Okay, so now we finally have our expression for G, and we know what all of these variables are. So now we can calculate what G is. G equals the numerator divided by denominator. The numerator is equal to GO plus GL times exponent Y equal to exponent Y Okay, so that's one way to solve for G. So that is the growth rate in millimeters per minute. Then it says, then state why you would be extremely skeptical about this result. Okay, so if you'll notice, our model was based on data in the range from 50 ppm to 150 ppm. So our model, which may not be exact, it probably, all we know is that it mostly represents how this relationship works in the range that we measured. Once you start extrapolating like hundreds of ppm away from where the model was set up, this empirical relation could be total garbage. It could not model the system at all. It could totally change. So yeah, I would be extremely skeptical in this relationship that we derived and just kind of extrapolating it out so far. So yeah, that's the answer to part B. Extrapolation, when you extrapolate that far, you can't trust the results in empirical models like this. Okay, so that is it for problem number 2.37. Thank you for joining me. Again, if you have any questions about this, comments, concerns, corrections, let me know, and I will try and address those in the comments. You have a request for a certain problem for me to do out of this book or from another book that I'm familiar with, let me know and I can try and work on those as well and make a video about that. Otherwise, I hoped to be able to see you in the next video. Thanks for joining me.